before I get into the physical properties and chemical properties, I just wanted to show you the molecular model of an alkyne, just so that you can see that it looks very linear. Remember from intro chemistry, the geometry right here, if you have a central atom that has two areas of electron density, it's very linear. It has a 180-degree angle here. For the alkene, remember, was trigonal planar and 120-degree angle. All right, you'll see a little bit of that in the lab when we do the molecular models. Okay, physical properties. Two main things we talk about are solubility and boiling point. The only thing that the hydrocarbons are going to be soluble in, these unsaturated or saturated hydrocarbons, is something that is very nonpolar. Because they are nonpolar molecules, they'll dissolve in a nonpolar solvent, meaning that they're not going to be soluble in water. Boiling point, remember, is affected by intermolecular forces. These are nonpolar molecules. They don't do hydrogen bonds. They don't do dipole-dipole, but they do a whole bunch of London dispersion forces. So since London dispersion forces are affected by the length of the molecule, the bigger the molecule, the more the London forces. So more surface area, more molecular weight, more London forces means higher boiling point. It's exactly the same as what we did in the alkene chapter. Now, the difference here is that now we have cis versus trans. Trans alkenes tend to have a higher boiling point than cis alkenes because they have more London forces. And let me show you why they have more London forces. You're going to be seeing this later on in the lipid chapter, because we talk about the difference between trans fatty acids and cis fatty acids. Here, let's talk about a trans. Here's a trans alkene. Okay, so this is 1, 2, 3, 4, 5, 6. This is trans 3-hexene. Why is it trans? Because these two hydrogens are opposite each other, rest of the molecule opposite each other on the double bond. Now let me draw a cis 3-hexene. So there's my cis 3-hexene. Let me see if you can see this. There you go. All right. Can you see that it has a bit of a kink to it? The trans looks a little bit more linear. So if you can stack up a whole bunch of these molecules and they'll London force. The surface area is bigger, so they will attract each other through London forces, therefore having a higher boiling point. With the cis, because of this kink, and like I said, we're going to be seeing this in the lipid chapter, it plays a very important role when we discuss the melting points of different fats. Here, because of this cis, it's going to have a lower boiling point because of this kink, not as big of a surface area. The molecules can't line up and London force as much. All right, so those are the physical properties. Let's move on to chemical properties. Now, unlike alkanes, alkenes can do a lot. They really can. They are a lot more reactive than the alkanes and a lot more interesting. So we're going to talk chemical properties of alkenes. Okay, they can do something called addition reactions. Remember how we said that the alkanes did substitution? Remember, the bromine substituted for one hydrogen, changed places. Well, with alkenes, they do something called addition reactions, where two things add right across the double bond. So basically, the double bond is made out of two bonds. One is a sigma bond, one's a pi bond. The pi bond is broken, and then you get these two things adding on. Don't worry about the terminology, sigma and pi. You do that in another class. But I just want to tell you, one of those double bonds, it's broken, and then you get these things adding on. So let me show you what I'm talking about. There are 4 different types of addition reactions. Number 1 hydrogenation. Okay, what is hydrogenation? Well, that is adding hydrogens across a double bond. So if you have a molecule like this, so this, excuse me, this is propene. I don't have to tell everybody it's one propene because obviously the double bond is at carbon 1. Because if I put it over here, it'll still be at carbon number 1 because you number it this way. So you don't ever put a number if it's an obvious done deal. You don't need to clarify. It's for sure carbon number 1. Okay, so this is propene. If I add a molecule of hydrogen, remember hydrogen is a diatomic molecule, so it's always 2 hydrogens. 2 hydrogen atoms make up 1 hydrogen molecule. If you add that, I'm going to put an arrow going down over here. Normally we do it this way, but I don't have much room, so I'm just going to draw an arrow here. You're going to need a catalyst for this to occur. It doesn't occur by itself. You usually need a platinum or nickel catalyst. And you need some heat, some pressure, and what's going to happen? The double bond is broken, and then these 2 hydrogen atoms add across that double bond. It's not a double bond anymore. And you know what? In order for you guys to see, I'm going to just do the result, the product over up here. So I'm going to put this here. Here's the product of the reaction. We're going to have carbon 1, carbon 2, carbon 3. Here are the 3 hydrogens. Here's this. Here are the 2 hydrogens. So I just copied this over here, but I broke one of the bonds. Now, this carbon needs a bond. This carbon needs a bond. These 2 hydrogens over here, one comes here and one comes here. So you just turned propene into, what is this called now? It's an alkane. It's a saturated hydrocarbon. This is now propane. Okay, so that's the first one. That's hydrogenation. Let's do the second one. The second one is halogenation. Remember I told you there are 4 chemical reactions, 4 addition reactions. Second one is halogenation. Well, just from the name, you know that it involves a halogen. So we're going to be adding halogen across the double bond. So here's my propene again. And my halogen is bromine. Again, halogens are all diatomic molecules. Each bromine is made up of 2 bromine atoms. Okay, now this one is instantaneous, no catalyst. It's going to work right away. Instantaneous. Okay, it'll work instantly, just like that. So when I add the bromine to the propene, double bond will break. Students will always ask me, does it matter which carbons I add the bromine to? Yeah, they have to be the carbons of the double bond. You can't just arbitrarily add bromines wherever. So they have to add them across here. So one bromine will come here. The other bromine will come here. And you're not going to add both bromines to one carbon because each carbon's allowed only 4 bonds, right? So what's the name of this thing going to be now? You've turned this alkene into a halogenated alkane. So what is this halogenated alkane now called? This is 1,2-dibromopropane. Ane, not ene anymore, because we got rid of the double bond, and now this is a 1,2-dibromopropane. Okay, so 2 more addition reactions. They are hydration and hydrohalogenation, and we're going to need a rule called Markovnikov's rule to implement those sometimes. So we'll do that in the next video. All right, see you in a bit.